So what we're going to talk about today is detection of organic compounds. So when you're going to be working in the consulting field or anything like this, you're going to have to deal with like detecting of it, finding it into the environment. So I wanted to talk a little bit about how we detect these organic compounds so you have a better understanding of the methodologies for them. So we're going to talk about GC and we're going to talk about HPLC. So what is a GC? GC stands for all these things are referred to as chromatography. And so in analytical chemistry, there's people who study this. This is their main area of research. Is how do we separate compounds? How do we separate things that are maybe even too close to each other? Remember I mentioned the xylenes, the O, P, and M. Well, what happens when you've got tons of them into there? Or how do you separate things that are very close to each other? Or is there faster ways, better ways, increased detection out there? And so chromatography is an analytical technique used for separating chemical compounds. And so its goal is to separation of that helps to determine the identity of the compound. So one of the things that we use is either GC, which is the gas chromatograph side over here, where we're using a gas, or we're using LC, which is a liquid. So we're either using gas or a liquid right now, and both of them are in there. And so we're going to talk about LC for liquid chromatography and how that works. And we'll talk about GC. So basically with a chromatogram, I've already kind of mentioned this before, you have a time along this way. So you have a signal that is coming out of your instrument. And it comes out with time. And then you have a signal how high the peaks go. So we can identify the compound by how long it takes. So if we know that the retention time here, this TR inside of there, is how long it's retained inside of the instrument, we can identify the compound. And then the area under the curve tells us how much. So we can use this as qualitative analysis, and we can also use this as quantitative analysis into there. And so you need to know the peak area, the area under the curve, and the peak height in this area, and what time it comes out in order to do both. So the first one we're going to talk about is a GC. Now we do have one here in the department, but we have a lot more over in the core facility over in chemistry. And so this is just the basics of one. And we'll go over the different parts of it. But basically what's going to happen is you're going to inject here in the injector your gas, your liquid. You know, you've used the hexanes in order to do like dissolves like. You put that in here. You've got a gas blowing through here. You've got an oven because it's gas. So we're looking at the boiling points of compounds. So this for GC, very important to look at the boiling point of the compound. So it boils, and then as it becomes a gas, it goes through this column, and then you read it into a detector into there, and then you get it and then you have a detector of some sort, and then a computer that detects it for you. So the first thing we're going to talk about is this column that's inside of there. Well, columns are, what it basically does is, okay, so you've got this go back here. So you have this injector, and you inject into an injection phase here, and so usually you inject like 1 microliter, something like that, into the system right there. And there's a little oven, and it heats up. And this oven, what it does is, as the temperature reaches the boiling point, so say you inject a liquid right here, because that's what you're going to inject, is either hexanes or some sort of liquid. It's going to stay right in here, and this oven is colder than this temperature. It's going to form a liquid, and it's just going to kind of hang here. But when all of a sudden this oven here turns to the temperature of the boiling point, all of a sudden this is going to go into this column and start running through the column. So this oven temperature really, it slowly ramps up. And so if you're trying to detect compounds with similar boiling points, you might like let it sit there. You might have like one that's at 73 and then one at 74, so you may sit at 73 for a while, then move up to 74 so that you can separate them out from each other. So you're using the boiling point, the property of the compound, in order to separate the compounds. And then you get into these columns, and I have here an example of a column, and I'm going to, okay, so I have a column here, so I wanted to kind of show you what this is and how this works and stuff. So this is a column from a GC. This is what's called a capillary column because it is really fine. So this is hard to show you guys in the thing here, but this is about the size of a human hair. So, you know, when I'm putting this and I feel like my hair here, they feel about the same width. So this is, you know, the diameter of this is about the size of a human hair. And there's actually, you can't see it in here, but there's a little teeny hole on the inside of it. So just imagine if your hair was a hollow instead of being solid. There's just this little teeny hole on the inside of this. So this is glass. It's a flexible glass, as you can see. I can bend it and anything like that. It's into there. And so it's very thin in here. The column itself wraps around here, and there's a whole bunch of lengths of it. So this is just one column itself, and so it goes all those. So it'd be like you taking one long strand of hair. This column itself is 30 meters long. So just imagine if you had a 30-meter long hair. Really long hair. But if you had a 30-meter long hair, you just wrapped it around here. This would make it just one continuous piece here. So the gas comes into here, and because of this length here, it takes it a while for things to go through this entire column here. This is another way of separating them. So what happens is on the edges of the column that are inside of here, these columns are coated with something that absorbs the organics. So what will happen is as the compounds are coming in here, maybe they have the same boiling point or close, very close, they'll come into here. Well, one of them might react more with the column, and so if it reacts and sticks and then runs and then sticks and then runs, it's going to be slowed down as it runs through here compared to a compound that doesn't stick to the sides. So we can separate out two things based upon either their boiling point, so when they enter the column, and then we can separate them by how they interact with the column material and how fast they can go in here. So the smaller the compound too, the faster it'll run through here versus the larger the compound. So you can get a separation of compounds based on size, the affinity. So like this particular column, it's called the capillary column. Its inner diameter is 0.25 millimeters. It has a 0.25 micron coating on the outside into them. And this particular one is designed for C8 compounds, so for gasolines. So what it is it's designed specifically for different types of organics. You can get ones that are better for benzene. You can get a generic column, which can be for anything. You can get ones that are for larger compounds in there. And so you can get these columns that can look for whatever kind of compound that you're interested in. And so this is just what a chromatograph column looks like. So what I was showing you was a capillary column. They could be long. The ones I have are 30 meters. They're very narrow tube. You could use these pack columns, which are short and 2 to 3 meters long. Really don't use those very much anymore. They are thermally stable because I mentioned temperature. So GCs are really good to go up to about 250, 300 degrees C of a boiling point of a compound. If they get too big, so when we start looking at some of the bigger organics, we'll talk about LC. Those are better for that. So GC columns need to be thermally stable, can handle any temperature from room temperature all the way up to 300 degrees and back down. And then they also need to be chemically stable so that no matter what you're putting into, they don't dissolve. Because you don't want to be like getting weird compounds coming off of your column and going, well, is that my column or is that actually in the aquifer? I was doing a project, and I'll explain at some point why I hate Baron Brockovich. But, and if you already know my story, great. But one of the things that happened with that one is they were testing water, and when they sent us the results from testing water in it, I was looking at the compounds they found in the water, and I'm like, well, your column is destroyed. You're just picking up everything from the column, not the actual aquifer. So very important part to that. So we also have detectors. So how does something get detected into there can also impact how we can find things. So you can find universal ones that detect all compounds, but you can also have ones that are very selective, so you're not overwhelming your detector with things and actually can work better for the compound you're looking at. So like an ECD here, which is electron capture device, you can see it up in here, is really great for halogens. Okay, so it's very, very good for those type of compounds. While a universal detector, like the T, total carbon detector? I don't remember what the T. You can know some of the stuff I never use. So the ECD we used a lot. But the difference between using, say, universal versus selective is the selectives are really very good at compounding your compound at very low concentration. So if you're really interested in one specific compound, you might want to be a detector that's really specific for your compound versus something that's just generic for everything. But for us in academia and for my lab, I usually use an MS or a mass spectrometer. We'll talk about what an MS is here in a few minutes. We usually use that because I don't know what compound you guys are all due for your research project, so we'll see how things go for that. And then you get these detectors. You want it to be very fast. You want it to detect it. You want to be able to detect it at a very low range, very low concentration in there. So some of the ones that we're going to be talking about, FID. FID stands for flame ionization detector. These are good for hydrocarbons because of the word flame. So what it has is a little gas flame that is there, and as the compound, the gas is going through the column and it comes out, it like blows it on top of this flame, and then there's a light reader that looks at the flame. And then if some hydrocarbon comes out, the flame gets brighter, more intense in there. And so it detects that. And so these are really great for gasolines, anything with a hydrocarbon in it. Very easy, very cheap. I mean, these things you can throw on the back of a truck and do it in the field because they're very, very hardy. So an FID is like a workhorse of a detector, very easy to keep going and stuff. Electron capture device I used a lot because I was doing TCE, so I was using for halogens. Into there's a little bit of radioactivity when it comes to those. So these other ones I really don't use, but you can see how they're quantifying and where they are on there. And so mass spec is one of the other universal detectors that is very common to use. So a mass spec is basically weighing a compound. So how much does a compound weigh? And then we're using that in order to detect it. So MS is an analytical technique for determining the chemical composition of a molecular structure. The sample is converted into ions and neutral particles by an ionization process. The resulting ions are separated according to their mass to charge ratio, M to Z ratio. Okay. So basically what you do is you look at these and you go, oh, okay, let's look at a mass to charge ratio of 15. Well, when you see something like 15, you go, well, okay, carbon is 12, hydrogen is 1. So let's see, 12, 13, 14, 15. Oh, because, carbon can have 4 hydrogens to be methane, but because these are ionized, you only get the 3. So you're going to get that little. So say you had a methyl groups on your compound. When it gets into the mass spec, what it does is it like excites it and then like breaks it up into pieces. And how it gets broken up into all these different pieces is very distinctive for that particular column, for that particular compound. So what you'll have here is you'll get a fingerprint of the compound, and these mass specs will be very unique for your starting compound. You will have like this M to Z15, that means it has a methyl group into here. You can calculate all these different other ones that are in here. And so what you'll have here is, 43 is the main ion that's in here, but you'll have plus or minus a hydrogen on each side because of how it looks. And so you'll get this mass spec, and then this mass spec you compare to a library, and it'll tell you, oh, there's a 95% chance this matches up with benzene, with whatever compound that you're looking for. When I first started doing mass specs, we used to have these giant books that we'd have to match up our chromatograms with to identify into there. Now it's just all done on the computer. It tells you and identifies it for you. And so you can identify the compound based upon how the compound is broken up inside of the mass spectrometer. So we have here is the chromatograph data. What it does is you'll get your peaks, and then if I click on one of these, it'll give me a mass spec onto it, and then I can identify what the columns are.